Hi, and welcome to H2.4 Newton's second law for rotational motion. In this lesson, students will be able to analyze the motion of a system undergoing an angular acceleration due to a net torque. If you understood that, then you're off to a good start. So let's talk about analyzing net torque again. Just as a reminder from yesterday, there's two possibilities. Either the object is in the equilibrium, where the velocity doesn't change, there's no acceleration, the net force is zero, or the object is not in equilibrium, and that's what we're going to be doing today. And when we did dynamics, we said, okay, it's not in equilibrium. That means the velocity is changing because there's an acceleration. That acceleration is caused by unbalanced forces, and the net force, when you add them together, is equal to ma. That's Newton's second law. The same thing is going to hold true. We did statics where we had balanced torques, so the net torque was equal to zero. Now we're ready to do problems where the torques are not balanced. The object is not in equilibrium. The angular velocity is going to change. There is an angular acceleration because the torques aren't balanced. And by the way, that opens the door for some interesting rotational kinematic problems, right? Because now we have an acceleration and we could use those rotational kinematic equations that we did in the previous unit. So the problems are going to get very interesting here. And instead of Newton's second law for linear motion, we have this rotational version where the net torque is equal to the moment of inertia, which we just learned about yesterday. It's like rotational mass times the angular acceleration. So, a review of Newton's second law. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction and inversely proportional to the mass of the object. And we said, okay, that breaks down to this formula where the acceleration and the force are directly proportional, the acceleration and the mass are inversely proportional. And then if you cross multiply, you get our nice F equals ma formula. It's the same thing, all right? That acceleration turns into angular acceleration, the net force turns into the net torque, the mass turns into the moment of inertia, and just like that. Now, it's important to note, the angular acceleration has to be in radians when you're using this formula. So where is Newton's second law for rotational motion? It's located right here. Okay, they give you the torque equals I alpha version instead of the alpha equals torque, net torque over I. And then it is in the section where it needs to be in radians. So the angular acceleration has to be in radians. No revolutions, no degrees, has to be in radians. So at this point, we've learned a lot of formulas. Okay, this is Newton's second law. And for the mass version of it now, like the moment of inertia, we have an equation for the mass now, which we didn't before. So depending on what the object looks like, that I term could be a bunch of different types of equations, a formula overload over here. So this, if you plug in this over here, the new formula looks like that. Wow, wow, wow. So we have a new formula for mass. Hold on a second. Didn't we also have a new formula for like the rotational force, torque? We didn't have really an equation like what is force? Force is just a push or a pull. Now, what is torque? It's the force times the lever arm. Oh man, so for all of these, you could plug in the force times the lever arm. Wow. These are all valid equations. Do you need to memorize them? No. All right, I don't want you to get formula overload here. For the formula for I, or the magnitude of I, will be provided for you, okay? And you'll have to use that formula when necessary. Sometimes they'll tell you the torque, sometimes you'll have to figure it out based on the force and the lever arm. The point is that I want you to focus on understanding the concepts instead of memorizing formulas, which students often do in physics class, where they're just plugging the numbers into the formulas and not really understanding what they're doing. If you understand the concepts, that's the point. Keep in mind that there are more equations than when we were doing Newton's second law, so it adds another level of, I guess, complexity to it. So we have like rotational force or torque. We have a new equation for that, as we said. And then for the moment of inertia, there's a bunch of new equations, all right, depending on what the situation is. But the same concepts hold true. The more torque, the more angular acceleration. It's a direct relationship. And the more moment of inertia, or rotational mass, if you want to think of it that way, the less angular acceleration, right? Because we said the more mass you have, the less acceleration. So let's get right into an example here. It says a grindstone has a moment of inertia of 8 kilogram meters squared. On applying a constant net torque, its speed becomes 150 RPM. That stands for revolutions per minute. Revolutions per minute in 10 seconds after starting from rest. Oh man, that looks like might be a kinematic equation thing. Starting from rest and then you're getting faster after a certain time period. Part A says, what is the angular acceleration of the grindstone? Part B says, what is the net torque applied to the grindstone? If you want, you could pause the video and try it on your own first before I do it. As a side note, I was looking for a better picture of a grindstone, and I came across this one. This is what they use to like sharpen knives and stuff like that. It's a very heavy stone, and it rotates. They use this lever down here with their foot to rotate it. And then as I was looking for the picture, I came across this nice poem. So you get a little poem with your physics today. Not often does that happen, but it happens sometimes. So the title is, If You Put Your Nose to the Grindstone Rough. If you put your nose to the grindstone rough and keep it down there long enough, you will soon conclude that there are no such things as a brook that babbles or a bird that sings. These three things will your world compose, just you, the stone, and your ground down nose. So I came across that, and then this article was talking about how, don't work too hard, try to keep things in perspective, enjoy life. There is something to be said about working hard and trying to work towards your goals, but it's about the journey and try to be happy in the present moment and that type of thing. So just wanted to share that with you. I thought it was a cool poem and a nice sentiment. But let's put our nose to the grindstone. Let's do some work. So what is this number here? Okay, hopefully the units stick out to you, and hopefully this sticks out to you. Moment of inertia. They're telling you what I is. It's flat out. So that makes our lives a little bit easier because we don't have to calculate it, even though it is a disk, right? If that was a solid disk, we have a formula for that, but we don't need to use that formula because we know the magnitude of the moment of inertia. We're ready to plug it into our equation. So there is a net torque, and they tell you, what is this? Revolutions per minute. That looks like angular velocity to me. Is 150 revolutions per minute. Okay, and then this is 10 seconds. Oh man, why do they got to do that to us? So not only is it revolutions, we got to be in radians, but this is 10 seconds. So we're gonna have to multiply by some conversion factors there. And then it says you're starting from rest. So we'll call this omega f. Omega I is 0. And you know what? We're gonna go rads per second because that's our goal. We want this to be rads per second. A says, what is the angular acceleration of the grindstone? So for part A, we're going to be looking for alpha. And for part B, it says, what is the net torque? You can write it like that if you want. Okay, so I guess the first thing is to make sure, the first thing that sticks out to me is I do not like these units. This is a revolution per minute. And just as a refresher, this is how I really want you to be converting your units. So let's get rid of the revolutions first and go into the radians. All right, so 1 revolution is equal to how many radians? 2 pi. And then we got to get into seconds. So let's get rid of these minutes. The minutes are on the bottom here, so we'll put them on the top here so that they cancel out, leaving you with seconds. and we know that 1 minute is equal to 60 seconds. So you do 150 times 2 pi divided by 60. These units cancel out, these cancel out, you're left with revolutions per minute. How many? 15.7. Oh, I said it wrong. Radians per second, not revolutions per minute. Radians every second. Okay, so we'll change that. And now we're ready to do part A. Let's think of a kinematic equation that we can use when we have the final initial angular velocity, the time, and the angular acceleration. We don't want the angular displacement. So lucky for us, that's my favorite formula because it seems to be the least complicated to me. Omega F is equal to omega I plus alpha t. No squaring needed, no like multiplying by a half. You're just plugging in the numbers here. 15.7, this is 0. Alpha is what we're looking for, 10. So you divide it by 10. The angular acceleration is 1.57 radians per second squared. And we're happy that it's in radians because now we could do part B, which is to find the net torque. Now, we don't know what the force is. All right, we don't know what the lever arm is. Do they tell us the radius of this thing? No. All right, they didn't give it enough information to do that. They did tell us the moment of inertia. So now we're thinking Newton's second law. All right, the angular acceleration is directly proportional to the net torque and inversely proportional to the moment of inertia. So the angular acceleration, or you could use the other formula. I typically like to use the version that's already solved for what we're looking for. So the net torque is equal to I alpha, okay? The net torque is equal to 8 times 1.57. So you get a net torque of about 12.6. 12.566, so we'll round it to 12.6. What are the units for torque? That's going to be a Newton meter. Okay, so in this situation, they were nice. They gave you the magnitude of the moment of inertia, but sometimes you'll have to calculate it. So in this problem, it says what must be the amount of tangential force that must be applied to the rim of a 2-kilogram wheel that is disc-shaped and has a radius of 0.75 meters in order to give it an angular acceleration of 4.8 radians per second squared. If you want, you could pause the video and try this on your own. Start by writing the givens and the unknown. So they're looking for the force. Oh, wow, I'm writing the unknown first. Okay, they're looking for the force. And the mass, it's a wheel. Okay, the mass is 2 kilograms. And it's disc shaped. So maybe you write down the word disc because we're going to use that in our look for the equation. And it says it has a radius of 0.75 meters. And you want an angular acceleration of 4.8 radians per second squared. Okay, notice that they're looking for the force. Okay, so our strategy is going to be, well, they gave me enough information to find the moment of inertia. They gave me the acceleration. I should be able to find the net torque. Once I know the net torque and the lever arm, because if you draw a picture of this situation here, here's our disk. All right, it says what must be the amount of tangential force. So the force is acting this way. This is the force. Well, what is the lever arm for that? If the axis is here, the lever arm is this distance, this perpendicular distance. Okay, so what is the lever arm? The lever arm is equal to the radius, which is 0.75 meters. I'm getting way ahead of myself, but that was part of my explanation of our game plan. So the game plan is to find the moment of inertia, use that moment of inertia and the angular acceleration to find the net torque. And then once we know the torque, then we'll be able to use the lever arm to calculate the force, because torque is equal to FL. Okay? So that's the idea. Let's do it. First step is to find the moment of inertia. And for a solid cylinder or disc, you look in your reference table, the formula is 1/2 mr squared. So the moment of inertia is equal to 2 kilograms times 0.75. Please do not forget to square that, and you get 0.5625, a long decimal. We'll keep it long since we're going to use it. You could put it in scientific notation instead. Just don't forget to write your units. Do you remember? Pause the video. What is the units for moment of inertia? Kilogram meters squared. Okay, great. So now we know the moment of inertia and the angular acceleration. We're going to figure out what that net torque is. Okay, so the net torque is equal to I alpha, MA, the rotational mass times the rotational acceleration, or the moment of inertia, times the angular acceleration. That's the right way to say it. So this is 5.625 times 10 to the negative 1. The angular acceleration is just 4.8 radians per second. That's nice. They could have given you revolutions per second squared or degrees per second squared just to add another trick in there. All right, so that's something to watch out for. Make sure your angular acceleration is in radians. So you take the answer you just got and multiply it by 4.8. And you get 2.7 Newton meters. Okay, so now we have 2.7 Newton meters, and we know that's equal to the torque, but the question is asking for the force. So we'll use one more formula, and we know that the torque is equal to the force times the lever arm. We said before that the lever arm is equal to the radius because the force is acting tangentially at the edge of the disc, and so that would be the perpendicular distance from the line of action to the axis. So now we know that this is 2.7 Newton meters. We're looking for the force. The lever arm is the radius, 0.75 meters. So you take your answer that you just got in the previous part and divide it by 0.75. Which gives you 3.6 newtons. Okay? Now, if you want a challenge, remember that slide I showed you with all the equations? You see how we did like 3 separate equations here? It is possible to combine these into one equation. So if you want, you can pause the video, I guess, and try that out. Or I'll just kind of give you a hint, okay? This is the torque, so you would plug that in over here. FL is equal to I 1/2 mr squared times alpha. And then there you go. It's a weird looking equation, but that's one equation and one unknown, and you could solve for the force that way as well. Either way is fine. Anyway, that's about it. Thanks for watching. Have a great day. Don't keep your nose to the grindstone for too long. Make sure you enjoy yourself as well. All right. Have a great day.